Okay. Got your test back. I'll post the solutions, but right now I just have my scribbled version, so I'll have to make kind of a good copy, and then I'll post that so that you'll be able to check. How I mark is everyone starts at 100%, and then I deduct marks. Kind of like Kramer's tip pile. Have you seen that episode of Seinfeld where Kramer puts a pile of bills on the table? So you start out with $100 tip and then he deducts it. That's kind of how I do my marking. Okay, so you don't have to build up to 100%, but you have to kind of keep your marks. Okay, and so what I want you to do, because so on each page, at the bottom of each page, and just make sure that that total at the bottom of each page adds up to the total on that page, right, with the deducted marks, because I don't double check those. And so if I'm going too fast or something like that, then it does happen that I kind of muck it up. Okay, and so I want you to check at the bottom of each page, because then I transfer those totals to the page on the front. Now the page on the front, if the total is circled, which it will be, it does mean I've double checked those marks. I enter the page marks into a spreadsheet and all that kind of stuff. And so so that one I'm feeling confident about. It's the transfer to the table at the front of the test that I want you to double check. The average was nice and high, 74.7%. For any sort of math course, that's considered quite good. And so I'm very pleased. I'm very proud of you. And I think most exciting today is the final exam schedule is posted. So usually we get advance notice that the final exam schedule is being posted. And then I heard it from a student last night. They're like, oh yeah, it's posted. What? It is? It's so exciting. And so our exam is nice and early, so you get it out of the way, December 9th. A beautiful time slot of 1 to 4. Very reasonable. And we'll be in E308. And then we say goodbye. Yeah, in the E building. Have you guys had classes in the E building? Okay, so it's the usually these rooms have a nice view, so that's kind of fun and distracting for the final exam. And so yeah, it'll be in the E building on the 3rd floor. Nice, but we've got a little ways to go before the final exam, of course. Any questions about the test, maybe, before we keep going? So like I said, I'll post the solutions. I just have my scribbled solutions right now. And if you haven't grabbed your test, they're up here. They're yours to keep forever. Treasure. You can frame it. A little bit. So of course, use it to study for the final exam. You'll get a redemption round on the final exam, right, on a lot of those problems. And so it'll be a good resource. All right. So let's see here. What did we review, or what did we introduce last day? We introduced polynomials. We introduced polynomials as f of x is, I'll write them in descender a subscript n times x to the n, because usually for polynomials, right, where we have multiple terms adding together, right? Some coefficient multiplying some power of x, okay, or some x to the power of n. We list them in decreasing order, right? And so we have something like a n, wow, I'm doing everything backwards today, -1 times x to the n minus 1 plus all the way down to a to the 3. Oh, I don't know what's going on today. A to the 2. Maybe I should do just 2 here, so I'd have enough room. A2 x to the 2, ax, and a0. And we talked about these special cases down here. Now maybe I'll just technically say 1. X to the 1, we don't usually write a power of 1 because it doesn't do anything, right? And a0 is technically times x to the 0, but anything to the power of 0 makes 1, right? And so that's how we create a constant. And we saw last day, oops, this little guy, n minus 1. What a mess there. We saw last day that if you wanted to remove some terms, all you had to do was set the coefficient to 0, right? That's allowed. And then they kind of disappear, but it's also how you reappear all the terms that are missing, right? Which we won't need today, but we will need on Thursday, kind of being able to fill out all the missing terms. Okay? And so we introduce some terminology, right? This is the leading term, and it determines the overall shape, right? We talked about the end behavior, right? And the leading term has a leading coefficient of an, right? But it also has degree n, right? Oops. Everything's hanging together today. There, degree n. And each individual term in the sum is called a term. Today, we're talking about quadratic functions. Now, quadratic functions are special cases of a polynomial. In fact, they stop at degree 2. Okay? And so quadratics are polynomials degree 2. Which means that a quadratic is going to look like this. F of x is a2 x to the 2 plus a1 x plus a0. So as soon as we have our highest power of x to the 2, we call it a quadratic. Now we know what x to the 2 looks like, right? Kind of a parabola, some sort. And depending on if a is positive or negative, it's either pointing up or pointing down, right? And so in general, quadratic looks something like this, right? A parabola, or it can look like this, or it can move up or down or to the sides, right? It can be stretched or any fun thing. Okay? But we know the overall behavior of a quadratic. Okay? So let's see here. I feel like there was something else I wanted to say here before I kept going. But, oh, that's what I wanted to say. So we also talked about kind of the short run behavior of polynomials last day. We're going to parking lot that. We don't need to reintroduce that, but we will talk about the vertical intercept, which we introduced last day, and we've we've seen before as well for lines, but the vertical intercept is where x is 0, right? So evaluate the function at 0. Let x equals 0. And the horizontal intercept we can have more than one, as we saw, right? But the horizontal intercept, and for a parabola specifically, right, we can have exactly one if it just touches down and it's got the end of the parabola on the x-axis. That would be one horizontal intercept. Or if we bump this guy up, right, something like this, then I would have these two horizontal intercepts, or I could have no horizontal intercepts. Huh? It's pointing up and it's been moved up. There are no horizontal intercepts. So we'll consider those three options today. But in general, right, it's where f of x is equal to 0. Right? And we have to find the x's that make it 0. Find x's that make f of x equal to 0. What's nice about quadratics is they will have a minimum or a maximum, right? And so if we have a minimum or a maximum, then we can say, okay, well, the largest possible value that I would want, right, would be the maximum, right? Or maybe I want to minimize something, right? I want to minimize the cost of something, maybe, right? Then that would be the bottom of the parabola if I can rewrite it as a quadratic. I really keep bumping this down here. I've got a lot to say, I guess. And so a nice property of quadratics or parabolas in general is that they'll have a minimum or a maximum. That they will have a minimum or maximum at the vertex. For the vertex, if I have a parabola that looks like this, the very bottom is the vertex, right? So this would be a minimum. Or what if I have a parabola that looks like this? Then I would have a maximum. So depending on the shape, right, we'll be able to minimize or maximize some function, some quadratic function. Each of these map to some value of x, right? Some value of x that minimizes or maximizes the function. So that's kind of neat. Let's see how we use it. Word problems, everyone's favorite thing. Not. I know. Everyone hates word problems. It's okay. To tackle word problems, first thing you want to do, especially on a test, is to draw out the scenario as you've understood it. Okay? Because that's the only way for me to really tap into your brain and think, okay, so if that's how you interpreted it, then did what you did next make sense, right? And so it's how you show me this is how I've interpreted the problem, but it's also a nice way to kind of plan your route, so to speak, in terms of your math. So let's read this, this problem here. A backyard farmer wants to enclose a rectangular space for a new garden. She has purchased 80 feet of wire fencing to enclose 3 sides and will put the 4th side against the backyard fence, which means she doesn't need to use any wire there. Find a formula for the area enclosed by the fence if the sides of fencing perpendicular, right, like this, to the existing fence have length L. Okay, so we've been told that there is some existing fence. Let's put it here. So we don't need to put a fence here. But we do need to put a rectangular garden up against this fence. So let's do something like this. Hey, it's supposed to make it all nice. No. Right there. So we've enclosed 3 sides. And the sides of the fencing perpendicular, right, perpendicular looks like this, as opposed to parallel, right? The side parallel to the existing fence would be this side, right? And so the side perpendicular to the existing fence has to have a length of L, and to make it a rectangle, they have to be the same. Now, she has 80 feet of wire, that's it, right? And so we've used a length of L as well as a length of L, which means that we have 80 minus 2L, right, left over for this side. So we get 80 minus 2L. I think that's the hardest part of this problem so far, is taking that total amount of wire and thinking about what you need to subtract in order for this total, this pointer, this total to add up to 80, right? But if you have 80 minus 2L plus L, you should get to 80. Okay, find a formula for the area enclosed by this fence. How do you find the area of a rectangle? Well, you know how to do that, probably. The area is one of the sides times the length, the width times the length, generally. Width times the length. Or the length times the width, if you prefer. Right? So just one of those L's. So we get A must be L times 80 minus 2L. Some version of that. A times B is B times A, so it doesn't matter. But I like to have kind of, if I have a small coefficient, right, just the L, I like to put it out front so I don't forget about it. Right, that's the only reason. Now, what's A function of? A takes an input of L, right? And so we could write this just a little bit fancier as A of L. Oh. A of L, right, takes an input of L and produces the area. And what I'm going to do is I'm going to expand this thing, and I get L times 80. Writing the coefficient out front, I get 80L minus 2L times L, which is minus 2L squared. Any variable such as L or X or anything, they'll behave the same way. Right? But what does this mean in terms of our graph? If L is the input, right, then that's going to go on our x-axis. Right? And if we rewrite this, because I'm on a new page now, with our decreasing powers, you want to make sure that you don't lose that negative, right? Because what does the negative do? It flips your parabola upside down, right? And so we have negative 2L squared plus 80L. And then technically plus 0 if you wanted to kind of see the full thing, right? But this is a quadratic. Surprise, surprise. Highest power of L is 2. And so what we know is this thing in general. Now, I'm not going to worry about the 80L. It'll do something, but in general, I'm looking at an upside down parabola. And so let's assume that it goes something like this. L is on your x-axis, and A of L, which is your output, the area, is on your y-axis. So what we'll see is that at some point of L, right, we'll be able to maximize the area, right? Because then the area kind of, it increases, it increases, it increases, and then at some point it turns, right, at the vertex, it turns, and it's decreasing again. And so that depends on what L is. Okay. So here at some L, we'll be able to maximize the area. We haven't been asked to do that. All we were asked to do, but I wanted to show you why we use quadratics most often, is find a formula for the area, which we have done already here. So I'll do a little check mark here, because that's all we were asked to do. For drawing this thing, right, if we were to sketch it a little bit more thoroughly, right, what could we do? We could find the vertical intercept. Where does it cross the y-axis? We could find the horizontal intercepts, right? Figure out where these points should be. And then it would be really useful to be able to find where the vertex is. Wow, what a segue, right? And so now we want to be able to find the vertex of a quadratic. So it will be useful to find, or to be able to find, the vertex of a quadratic. For sketching, but also for solving problems like what value of L, right? What length should she set those perpendicular sides to be in order to maximize the area of her garden, right? So then we need to find the vertex. But before we can do that, we've got two different forms of quadratic functions. The standard form is the form that we've been working with. Instead of A2 and A1 and A0, we've replaced it with ABC, right? Just because it becomes a little boggy, and because we only have 3 coefficients. So notice here, right? This is instead of f of x is equal to a2 x2 plus a1 x plus a0, right? We just replaced it with ABC. Now your formula sheet will use ABC, and so that's why you want to make those links. A, B, and C. You've probably seen the quadratic equation, right? Negative b plus minus the square root of b squared minus 4ac over 2a. We'll introduce it again, right? What does that do? It takes a quadratic that has this form, ax squared plus bx plus c, and it finds the values of x that make the function 0. Had to be careful I didn't reverse those. Which would be what? The values of x that make this function 0, those are your horizontal intercepts, right? So that's what the quadratic equation does. But we're getting there. A form that we're probably not so used to, but which is nice, is called the transformation form. And so the transformation form of a quadratic looks like this. It has an a out front, similar to our a up here, right? But then we have an x minus h squared and then plus k. Notice how we've introduced an h and a k as opposed to our b's and our c's. Now the vertex of the quadratic function is at hk. And so if you're able to rewrite your equation into this form, so from this standard form into this form, right, then you'll be able to quite easily find the vertex, right? Here we can see, okay, h and k at x equals h and y equals k, that will be your vertex. And so because this has the vertex in it, sometimes it's called the vertex form. Now, what I want to do is write the transformation form. I'll call it the transformation / vertex form in standard form. So as an exercise, I want to rewrite f of x is equal to a times x minus h squared plus k, and I want to expand it and rewrite it so that it has this shape of ax squared plus bx plus c. Because that way we'll be able to find the linkages between them. And I want to move in this direction because moving from the standard form to the transformation form is not nearly as easy, as you'll see. But this way, we can handle this way, right? As long as we remember that x minus h squared is x minus h times x minus h, right? That's a good first step in expanding this thing. X minus h times x minus h, and then plus k. I'm going to leave my a outside for just a little bit longer, and I'm going to focus on my x minus h squared. Make sure you use brackets because that a is multiplying all these terms. X squared, and then I've already confessed that I am not very efficient when I expand these. I feel like I always have to do all 4 terms, right? Some of you are really good at expanding these quickly, right? And that's okay, that's great. But you'll just have to put up with my slowness, right? X times x plus x times negative h is minus xh minus h times x. Now, in order to collect like terms, I like to have the x on the outside or write them in the same order, right? Because x times h is h times x, right? Or you can just see that. Minus xh, and then negative h times negative h puts me at plus h squared, and then plus k. Remembering that that k is not being multiplied by a. So, simplifying, I get x squared minus 2xh plus h squared, then plus k. I can expand that a inside. Ax squared minus 2axh for some version of that. I'll rewrite it later. Plus ah squared plus k. Why did I say I would rewrite it? Because my x's, in order to have this form, right, I want to have a coefficient times my x, right? A coefficient times my x, and then just the coefficient on its own. And so ax squared looks good. It's my minus 2axh. I'm going to rewrite it as negative 2ah times x, right? Just so that the negative 2ah is one thing, right? Those are just numbers. And then ah squared plus k, that'll just add up to a number, right? Our last coefficient. So we get minus 2ahx plus ah squared plus k. So notice, it's a bit of a stretch, right? A equals A in standard form. A stays as A, right? Which is why it got to keep the A in the transformation form. B, right, in the standard form, it's ax squared plus bx plus c, right? ax squared plus bx plus c, which means that b must be negative 2ah times x. And then this whole chunk, c, must be ah squared plus k. Nice. If you wanted to go the other way, it'd be a lot harder because you would have to, out of thin air, say, oh, I'm going to let A be A, and then I'm going to try with B equal to negative 2AH. And already there's no really rhyme or reason why I would do that, right? But it is somewhat easy to see that if you expand this thing, then you can rewrite it as ax squared plus bx plus c. Okay, let's remember what h is. H in your vertex is the x coordinate at the vertex. Right? And so recall H is the x coordinate of the vertex. Well, if we have an equation in standard form, ax squared plus bx plus c, what do we have? We have a, b, and c, right? And so what if we're able to solve for h in terms of a and b? That might be nice. Right? And so here we know that b must be equal to negative 2ah. So what if we solve for h? Well, I get b divided by negative 2a is equal to h, or some version of that. Negative b over 2a, maybe. Okay. We don't really need to solve for k. Why? Ba-dum-pum. It wasn't a ba-dum, it was a ba-dum-bum, because it's the y coordinate. If we let x be h, right, then the k is the y coordinate, which is the function evaluated at h. So that's cool. We could use this equation here. It does have a c and an a, and now we have h in terms of a and b, and then we could solve for k, right? But I think it's actually easier to just remember that, okay, if I have h, then I use h as my input, and I can find the output. So then I'll also say that recall that k is the output of the quadratic at x equals h. Oh. So you can solve for k if you want to, but we only really need the h. Where is it? I'm gonna move this up here because I've already kind of introduced it. We did all that work. We may as well introduce it now. And maybe I'll put it here. For a quadratic given in standard form, right, ax squared plus bx plus c, the vertex hk is da-da-da-da, right? This guy here. H, we've floated the negative out front, just make it a little bit cleaner, right, is negative b divided by 2a. And then, like we said, well, k, we can solve for k, but we don't really need to, right? As long as we remember that k is the function evaluated at h, right? So as long as you're able to solve for h, then you can evaluate the function at h. Okay? Remembering that h is negative b over 2a, right? That's the same as evaluating the function at negative b over 2a. And so here, that's what this guy is saying. So if you have an equation in standard form, let's remember standard form is f of x equals ax squared plus bx plus c. right? Then you can find the vertex, right, by finding H. This, of course, I actually didn't confirm it, but I'm confident it's on your formula sheet, which means you don't have to do that, but it's fun and it's nice to see where it all came from, right? But as long as you know that you can go from the standard form and you can still use those coefficients to find the vertex, then I'm happy. Right? So, nice to see where it came from, but this is on your formula sheet. I'm confident. Here it is. Nice. You have to find the vertex of something like this, right? Then it might be helpful to recognize that this is in vertex form or transformation form, right? And so here, right, if we were to map this to either standard form or transformation form, I can map this easily to the transformation form, which has H and K, which is my vertex. So let's see here, copy. I'll see if I can kind of line these up there. So this is in transformation form. Which tells me that, or maybe I should do the arrow the other way. A equals 2. Making sure that you're checking that there's a minus, right? Because in the general form, there's a minus, which means that if there's addition here, then your H is negative, right? Because that's how we get addition, right? And as long as you've got a square out here, then you're able to map this H equals 3. And in this case, right, plus K. So again, if you have a -1 here, for example, then K must be -1, right, in order to be a plus K. And so then K is 1. The vertex is at HK, which in this case is at 3, 1. This 1, even if we weren't given it in the problem, right, this is f of 3. Right? Put 3 into the in as the input, and the output should be 1. Right? And so if we put in f of 3 into 2 times, I'll do x minus 3 squared plus 1, I get 2 times 3 minus 3 squared plus 1, which is 2 times 0 squared plus 1. 0 squared is 0, 2 times 0 is 0, and left at 1. Right? Nice. So as long as you remember that that K really just follows from H, right? You just evaluate the function at H. It's going to make our lives a little bit easier. Since we know that this A, right, this A in transformation form is the same as the A in the standard form, right? And what do we know about A? A determines, right, if A is positive, then the parabola is pointing up, and if A is negative, then the parabola is pointing down, right? And so A determines kind of the overall behavior, right, up or down of this parabola. Knowing that, in this case, A is positive 2, which means that this is going to be a parabola facing up, right? Which means that this vertex must be the minimum, right? If the parabola is pointing up, right, then it's at the minimum. So we have something that looks like this. Oops. So we're told here at 3, 1, we have the vertex and it's pointing up since A is positive 2. And we could do work and we could find where the vertical intercept is, but we won't worry about that. Right? So that means that the vertex is a minimum. And I think the lines were different before. I've added in an example. What if we have to find the vertex of f of x is negative 3 times x plus 2 squared minus 1? So now, again, let's see if I recognize that this can be mapped to the transformation form. And so that's nice because our goal is to find the vertex, which is at HK. Right? A is negative 3. So already I know that this is a parabola facing down. Right? H, if it's x plus 2, then H must be negative 2. Right? And K, if it has to be plus K, but I have minus 1, then K must be negative 1. And so I have A equals negative 3, H is negative 2, and K is negative 1. Being careful when you map those. Huh? For the vertex is at negative 2, negative 1. And then a follow-up question could be, is this a minimum or a maximum? Right? And so since A is equal to negative 3, the vertex is a maximum. Just because we'll have something that behaves like this. Now, negative 2, negative 1 puts me somewhere down here, right? Vertex. And I know I would have something like this. And again, you can confirm, oops, I wanted this orange. Confirm by taking the function at -2, right? The output should be -1. F at -2 is -3 times -2 plus 2 squared and -1. -3 times 0 squared plus, or sorry, -1. Just gonna mess it up. Is -1. Nice. What if we have to find the vertex of 2x squared minus 12x plus 1? Now, this is in standard form, right? And so I see that A is 2, B is -12, right? Because it's plus bx plus c. And so B must be -12 and C must be 1. Now we've already established, right, from earlier, recall that H, which is the x coordinate of the vertex, is -b divided by 2a. I'm going to confirm that, but I think so. H is -b over 2a. Okay? So if I have b and a, then I can solve for h. Making sure you keep that negative. Negative out front, b is -12 in this case, divided by 2 times a, which is 2. So I get -12 divided by 4, which puts me at -3, but then I have the negative out front. So then h, I'll say is -3. So h must be 3. If h is 3, right, and we know that this thing is pointing up, right, because our a is positive, right, then I know that if I had to sketch this thing, right, then I would be here at h equals 3. The parabola is pointing up, so I'm going to put it somewhere with a pit at 3 something. Oh. So my k is really just the function at h equals 3, right? I have the function g of x in this case, so I need to evaluate the function at 3. So here, g of 3 is equal to k. So g of 3 is, I'll do 2x squared minus 12x plus 1 so I can scroll up, is 2 times 3 squared minus 12 times 3 plus 1. I'll do, therefore, k is equal to this. G of 3 squared is 9 times 2 puts me at 18 minus 12 times 3, 24, 36. Math. Plus 1. Uh-oh. Now I'm hooked. Need my calculator. I had to think too hard. for the 2, 3 squared? How about negative 17? Which means I sketched it wrong, but that's okay. Has the same behavior. It's obvious that should just be on the negative 17, just bump it down. Right. So then, how can I really what it should look like? It's like this. Negative 17. Same idea. It's not until you have that K, you know. So therefore, the vertex, the vertex is at HK, which in this case is 3, negative 17. And as a follow-up, since A is positive, this is the minimum of the function. And since A is positive, the vertex is the minimum of the function. Yeah. So now, if we go back to our garden example that we started with, right, what value of L maximizes, when we're trying to maximize or minimize a function, that's called optimization in general. And what's really fun is UBCO has a really, really good optimization program. So optimization is a subfield of math. They're just constantly trying to optimize stuff, maximize, minimize, not just quadratics, but fancy things, right? But at its core, we are doing optimization problems, right? So what value of L maximizes the area in the first example? Okay. So now we want to go back and snag the quadratic that we created, the monster we created, this guy here. Okay. And from our introduction, right, we said, okay, well, I should have, right, I have a parabola pointing down. And so I know that I'll be able to maximize the area, right, at some value of L, right, at the vertex. So I'll grab all of this and then I'll erase what we don't need. It's easier. There. Right, so we've already seen this. And we know it's a quadratic now. And we don't really need the C on there. So now we want to find this vertex. Right? But in order to find the vertex of something in standard form, right, we first need to list what our A, B, and C are. Right? And so here, A in this case is -2. B in this case is positive 80, and C in this case must be 0. Oh. Our vertex, H, our x-coordinate of our vertex, H, is -b divided by 2a. which means that h happens at negative 80 divided by 2 times negative 2. So I get h must be negative 80 divided by negative 4. Negative over negative makes a positive, and 80 divided by 4, I'm going to go for 20. Which means that L equals 20 is going to maximize the area. If you think about it like that, then of course a follow-up question would be, well, what is the maximized area? Right? You're limited to 80 feet of wire, right? You've already determined that, okay, if I force the length of the perpendicular side to be 20 on both sides, then I know what my width has to be, right? 20, 20, take away 40, then I have 40 left, right? And so then I can find my area. Or if you want to get fancy, A of 20 is negative 2L squared plus 80L. Yeah, so I don't have to scroll around. Negative 2 times 20 squared plus 80 times 20. Better use my calculator. I get 400 times negative 2. But, oh, I did 80 plus 2 and I was stumped. Thank you. I was like, yeah, that sounds good. So I get an area of 800, which checks out, right? If we have our existing fence and then we're saying, okay, force this to be 20, because that's what we found, then this must also be 20, and this must be 80 minus 40, which is 40. So the area is 20 times 40, which should be 800. Whew. Good. Nice. Okay. Weird. For some reason, last year I only got to here, but we got lots of time. So I don't know what happened. So speedy. Maybe you guys are just nodding along too much. Oh yeah, encouraging me. You got this. All right. So, good. Let's do, now this one is a bit of a beast. And what I want to do is just give you an opportunity to try sketching it out. You don't have to solve it because we'll solve it together, but just try sketching out how you would interpret this thing. Right? And it's just for you. I'll do it with you in a bit here. But let me just that page. But because sketching out the problem is arguably the hardest part of a word problem, I want you to try.
It's semicircle thing that's surrounded by a semicircle. That means like a semicircle top in the bottom.
Oh. Oh. Exactly. Mm. Sorry. R squared, right? This one's a pickle, isn't it? I guess I should remind you that the perimeter is the outside. Right, so starting here, it's the length of the entire outside. And just as I promised, hopefully I have these. The area of a circle is pi r squared, right? The perimeter of a circle to pi r. My job to remember this.
Also do I equals B, or sorry, this one is up to-
Oh, pi d. Yeah, you can. Usually we do it both in terms of r, but yeah, 2r is d, which is the diameter. Nice. But there's also a method to my madness using r. Why? Why? Because if I have r, I'm going to latch on to this r, right, and incorporate it into how I solve this problem, right? Specifically from the center out to this edge, I know is going to be r, right? And so I drew a rectangle, surmounted, sur means on top, so surmounted, mounted on top by a semicircle, right? And so a semicircle on top of a rectangle. And we want to force this perimeter, so the length of the entire outside to be 40 feet, 40 units, whatever. We want to know what dimensions will maximize the area, right? And as soon as you have a circle involved, it's usually a good idea to write things in terms of the radius, right? Because if this length is r and this length is r, then what must this length be? 2r. That's a nice place to start, right? Trying to avoid incorporating more variables than you need to, right? So trying to keep it in terms of r as much as possible. Yeah. Okay. So now I have, ultimately I want to maximize the area. Now the total area is going to be the area of this rectangle plus the area of this semicircle, right? And so that's why I incorporated the area of the circle. Now we only have half a circle, so we can divide that in half, right? But we'll parking lot that for later when we talk about the area. How about the perimeter? The perimeter of the circle, the full circle, is 2 pi r, which means that the perimeter here is going to be 2 pi r divided by 2. Right? And so here, this perimeter, I'm going to run out of colors pretty quickly here, but this length here must be 2 pi r divided by 2. Now, what's really nice is that's just pi r, right? And it's still in terms of r, which is also a good get. Right? Now, what's left, right? If we've got this as 2r, so this length is taken care of by 2r, and this length is taken care of by pi r, right? And I only have a perimeter of 40 feet, right? Unless you want a wonky window, right? These two sides should be the same length, right? And so let's figure out how much length we have left after we take away 2r and pi r, right? And so these sides each, or yeah, let's do that. Each side must be, well, I have 40 feet. Let's start there. And then I've used up pi r for the top, whatever pi r is, depending on what my r is, right? I've used up pi r for the semicircle, and I've used up 2r just because of how circles behave on the bottom here. And so minus 2r, and I have two sides, so I need to divide this by 2. All of it. Now what's nice is you can collect like terms, remembering that r is your variable, right? And so you've got pi, which is just a number, and you've got 2, which is just a number. And so really what we're left with here is we have 40 minus, I guess you could do plus r. What's going to be better? Let's try it, pi plus 2 divided by 2. I've pulled out a common negative r. I'm still waffling. What am I waffling on? This would be equivalent to 40 plus r times negative pi minus 2 divided by 2. I think it's a little bit cleaner to have the minus r. Debatable. I'm open to debates. I'm going to keep my go-to version here. But if you wrote it like this, the results would be the same. Now, pi plus 2 or negative pi minus 2, that's just the number, right? So don't be thrown off by that. But also be careful that you don't try to cancel 2's here. Why can't you do that? Because you've got a pi plus 2, you would need a multiple of 2. If you were able to pull out a minus 2r here, that would be nice, right? But we can't, because then you can do 40 divided by 2 minus 2r divided by 2, but we can't. Well, technically it's pi, so I'm going to keep pi. I know. At the end, we'll do some rounding, but there is a pi button on your calculator, so. But I think then you get a nicer number. Yeah. Then it's okay. When you guys use pi in your other courses, do you just use 3.14 or do you use the full constant? Or maybe you don't use pi yet. Haven't used pi yet? Well, it's good to learn how to use it properly then. And then you can enjoy it when they just tell you to use 3.14, which I think they will, but because it happens. So I'll say that this, you could do it like this. Your results would be the same, but I'm gonna stick to this version here. That's a little bit mucky, right? And so, okay, now I have each side has a length of 40 minus r times pi plus 2 divided by 2. Great. Now, what was the goal? You want a Norman window with a perimeter of 40 feet, which we have forced, right? And so what dimensions will maximize the area? So we want to maximize the area. So now let's tackle the area. The area is going to be the area of the semicircle plus the area of the rectangle. Is going to be the area of the semicircle plus the area of the rectangle. The area of the semicircle is going to be, well, the area of a full circle, pi r squared, right, is going to be pi r squared divided by 2. Plus the area of a rectangle. Should be easy, but one of the sides is this monstrosity. That's okay. All right, and so we'll do the length of one of the sides times the width, which is 2r, which is nice. And so I will do 2r on the outside so I don't forget it. And then times 40 minus r times pi plus 2, all divided by 2. Now, I can see right away that I could cancel these 2's, right? Because I've got 2 times something over 2. But I also am trying to add fractions here. Now, to add fractions, I need a common denominator. And I already have a common denominator of 2. So I'm going to hold off on the cancellation for just a little bit longer. No harm if you ended up canceling here, but then you would have to say, oh, I need a common denominator. Then you'd have to force a common denominator of 2 anyways. Right? And so it doesn't matter which order you do it, but let's see here, I'll highlight, right, to add fractions, we need a common denominator, which we have. So now, what can I do? Pi r squared plus 2r times 40 minus r times pi plus 2, all divided by 2. I can simplify this, right? Definitely.
Isn't the 2r outside the bracket, so it is still, in the bracket?
This guy?
Yeah.
It is, because this divided by 2 can kind of float around, because technically, if you didn't have it down here, you would have times 1 over 2. And so because they're multiplying, it's over the 2. I better remove that because that might be confusing later. Okay. Now, when you're expanding this, slow and steady wins the race. I'm going to first expand this negative r inside, right, times the pi plus 2, and then I'll expand the 2r, right? Because if I try to do it all in one move, I think I know myself and I know I'll miss a negative or something, right? So here we go. I mean, technically you could use this, but it doesn't really look like a nice quadratic to me yet, right? So pi r squared plus 2r, I'm going to keep that on the outside for a little bit longer, minus 40 minus, I don't know why I said that, minus r times pi minus 2r. And then don't forget to divide by 2. And now I'll expand the 2r into those brackets. Pi r squared plus 80r minus 2r squared pi, or 2 pi r squared if you prefer. And then minus 4r squared, all divided by 2. I can collect like terms. What I'll do to emphasize that I'm collecting like terms is I'll rearrange this with all my r squareds at the front, right? And then all my r's and constants at the end. So I get pi r squared minus 2 pi r squared, rearranging those so they match, minus 4r squared. Throw some brackets around that, why not? Plus 80r. Make sure you've nabbed all the terms. Pi r squared minus 2 pi r squared minus 4r squared plus 80r. Looks okay. And then all divided by 2. You don't want to forget that guy. Now, I can pull out a common r squared. Why would I want to do that? That's going to give me a, right? It's going to be a big nasty a, right? Value for a, but that's okay. And so we definitely added pages for work there. I get r squared times pi minus 2 pi minus 4 plus 80r divided by 2. It is cleaning up pretty nicely, right? Pi minus 2 pi is negative pi. r squared times negative pi minus 4 plus 80r divided by 2. Still can't cancel that divided by 2, but you can rewrite it in terms of ar squared plus br plus c, right? So we're allowed to, as long as you keep both fractions over 2, you're allowed to split the sum up again, right? And so what we have is we have negative pi minus 4 divided by 2. That's one number. Okay. And it is a number. Right? Negative pi minus 4 divided by 2. If you do it on your calculator, you just get a number. Times r squared plus 80 divided by 2 times r plus 0. I'll bump these down. Here, a is negative pi minus 4 divided by 2. So a is going to be approximately, let's see here, negative pi, then minus 4, and then divided by 2. Roughly negative 3.571. Rounding way too early for my liking. It's negative 3.570796327, but close enough. B is 40 and C is 0. A is negative, right? So I know I have a parabola that's pointing down because it's negative. So that means that at some value of r, I'll be able to maximize what? Maximize the area, right? Which is a function of r. Right? And you know what I should do for completeness is under the area, I should rewrite it as the area as a function of r because r is the input. Right? And so here, since a is negative, the vertex will be the maximum of the area. So we need to find the vertex. The vertex we know is that h is negative b divided by 2a. And let me just get this out of the way here. If I have A, B, and C, then it's relatively easy to find the vertex. I'll use, now you are welcome to use the negative pi minus 4 over 2 as the exact number, of course, but I'll use the approximation because our radius doesn't need to be so perfect. Negative 3.571. If I do negative 40 divided by negative 3.571, I get an H of 11.2 0.101. Okay, I can't handle it. Because I used an approximation here, then my results are an approximation. That's more of a personal pet peeve than anything else. Question?
You're supposed to be TLA on the bottom.
Oh my gosh. And I'd already committed, which means I have to write it in red. The punishment. 2. Still an approximation, but yes, thank you. Oh boy, 2 times negative 3.571, still using the approximation, negative 40 divided by that. .600. Let's do 0.1, since it's an approximation anyways. Thank you. Which means that, okay, H is the x coordinate of the vertex, but the x is the input, which translates to a radius of 5.601 roughly, or 5.6 inches. Units, who cares? Feet? 5.6 feet? I know, I'm bad. All your other courses, I'm sure. They're obsessed with units. Not me. I'm not. I'll say feet. Huh? So therefore, the area will be maximized at R equals, I'll do roughly 5.6 feet. Feet is weird because 5.6 is not 5'6", right? But 5.6, so be careful. Which means that we get an area of what? Well, we found the formula for the area in terms of R, right? And so we can jump down. How about right here? Let's grab this so I don't have to scroll around so much. Let's do it like this. A of R. I'll keep the +0. You don't need the +0, but nice. So at A of 5.6, wherever you see an R, you're going to replace it with 5.6. And if you were to use the approximation here, right, the negative 3.571 or whatever we got, yeah, that's okay too. It'll be roughly the same. Times 5.6 squared plus 80 divided by 2 times 5.6. Let's see here. 5.6 squared times bracket negative pi minus 4 bracket divided by 2 plus bracket 40 times 5.6. I get an area at 5.6, a radius of 5.6 is going to be roughly 112.0198272 square feet. because it's an area. So the area is maximized to roughly 112 square feet if we force the radius to be 5.6 feet. Nice. That one is a pickle, but that's as hard as we're gonna make it. And hey, we've already basically introduced this, so may as well finish it. Wait. Because we've already talked about the intercepts, right? The vertical intercept is, hey, where it crosses the y-axis, right? And we could have a scenario where we have 0 horizontal intercepts. We could have exactly 1 horizontal intercept. So if the vertex is at y equals 0, then you have 1 horizontal intercept. Or most of the time we get 2 horizontal intercepts. Right? And so again, the vertical intercept is kind of a nice one. The vertical intercept is at f of 0. Right? So you want to evaluate at x equals 0, and that's nice and usually quite easy to do. Now the horizontal intercept potentially more than one is where f of x is equal to 0. So the values of x that make 0, make the function 0. If f of x is a quadratic, we use the quadratic equation to find the horizontal intercepts. Which says that x, right, the values of x that make the function 0 is negative b plus minus the square root of b squared minus 4ac divided by 2a. Now, for some reason, I don't see it in here. Maybe later. I know I already pre-filled. I suspected I wouldn't have time for those. I'll grab it from the formula sheet because the quadratic formula or the quadratic equation, is on your formula sheet. But for some reason, it's not in your notes. That's okay. I'll add it in now. Negative b plus minus b squared minus 4ac divided by 2a. Everything's going to hinge on b squared minus 4ac. There are 2 options, or sorry, 3 options. All right. So if b squared minus 4ac is greater than 0, right? You can take the square root of a number, and then you'll have negative b plus minus 2 numbers, right? So that'll give you 2 horizontal intercepts. Versus if b squared minus 4ac is equal to 0, right? Then you have negative b plus minus 0. So then you're just at negative b over 2a. Well, that sounds familiar, right? That sounds like the x-intercept of the vertex, which tells us that the vertex is on the x-axis, right? Which means that you have 1 horizontal intercept. remembering that you cannot take the square root of a negative number, right? Then that value does not exist. So then if b squared minus 4ac is less than 0, then that just tells you that it has 0 horizontal intercepts. It's just above or below the x-axis and will never cross. And that's okay, you can find that. Okay. I only have 2 here, so can do it. As long as your equation is in standard form, it's easy enough to find the horizontal intercepts. We want to find the horizontal intercepts is where f of x is equal to 0. We can use the quadratic formula, which says that that happens at x equals negative b plus minus the square root of b squared minus 4ac divided by 2a. Which means we just need to nab our a, b's, and c's. A is 2, b is 5, and c is negative 3, making sure you keep that negative. Right. Plugging those in, I get negative 5 plus minus the square root of 5 squared minus 4 times 2 times negative 3 divided by 2 times 2. Plus minus 25 minus bracket 4 times 2 times negative 3, I get 49 divided by 4. Square root of 49 is 7. So this can simplify to negative 5 plus minus 7 divided by 4. Negative 5, I like to start with the minus because that'll give me the left-hand value and then the plus gives me the right-hand value. Doesn't actually matter, but it's nice. So x is negative 5 minus 7 divided by 4 and negative 5 plus 7 divided by 4. All right. Because we can take that square root and find that it's 7, we get 2 horizontal intercepts at negative 5 minus 7, x equals negative 12 over 4, or negative 5 plus 7, 2 over 4. Or if you want to simplify, x is equal to negative 3 and 1/2. And we wanted the vertical intercept as well. But that one's easy. What's our function f? The vertical intercept is where x is equal to 0. 2x squared plus 5x minus 3. Oops. Two times 0 squared plus 5 times 0 minus 3 puts me at negative 3. Of course, the benefit of knowing the intercepts, right, and where the vertex is, maybe, and if it's pointing up or down, right, that'll tell us what a reasonable sketch would look like. Right. I'll leave this one for review on Thursday, and we'll pick up there. But I also have some more examples that you can try with just the solutions that I've added in already, that'll be in the notes. But if you have any questions, let me know. Otherwise, I'll see you on Thursday. I'll say use for review on Thursday. Stop this.